Now, I should introduce Mahmoud Shakiba has been doing exceptional work in spatial data analytics in the area of characterization, modeling, and forecasting with fractures. Now, we know fractured reservoirs are quite common. These spatial patterns are complicated and multi-scale, and Mahmoud's been developing exceptional research to be able to deal with this setting. Mahmoud, I don't want to steal any of your thunder. I'll go ahead and let you go ahead and get started. Thank you very much for joining in.
Thank you so much for the opportunity. So can you see my screen and hear?
We can see it, Mahmoud.
Okay. So hello, everyone. Thank you very much for your time. My name is Mahmoud Shakiba. I'm a PhD student of petroleum engineering, and my supervisors are Dr. Larry Lake and Dr. Michael Birch. So this would be a quick presentation on my research work on spatial characterization and modeling of fracture networks using point processes. First, I would like to thank the FRAC research group at the Bureau of Economic Geology for funding this project, and Dr. Gale, Dr. Labeck, and Dr. Olson for their guidance and support. So the objective of this research work is to introduce new spatial data analytics for characterization and modeling of complex fracture networks. Some of the conventional approaches or methods that are used in the industry to spatially model fracture networks rely only on the histograms, or basically the distribution of the fracture length and the distribution of the fracture orientation or strike angle. So the idea is that if we know the distribution of the fractures in terms of the length and the orientation, that should be good enough to make or generate a representative model of the fracture networks in the subsurface. But it turns out that's not accurate because, for example, in this example, these two fracture sets, set 1 and set 2, have the exact same distribution for fracture length shown on the left-hand side, and the same Rose diagram and the distribution for the orientation. But as you can see, they have completely different spatial characteristics. In set 2, fractures are connected over the entire study domain. The connections between fractures or the intersection points are shown with red dots. But the set number 1 on the left-hand side, it has only a few intersection points, or the connectivity is much lower than the set 2. So although they have the same distribution in terms of histograms, they exhibit different spatial characteristics. The same problem exists for 1D application as well. So these two fracture sets, set 1 and set 2, they have the same or exact same distribution for spacing between fractures. But as you can see, set 1 is more or less randomly distributed, but in set 2, we have a major cluster in the middle. So some of the conventional statistical measures that are often used in the industry, such as histograms, actually fail to capture the spatial distribution of the fractures in the subsurface. Another complexity with modeling fracture network is that they exhibit a multi-scale size distributions. So if you plot, for example, the spacing between fractures or fracture aperture size or fracture length, often you see that they span across multiple length scales. So the statistical methods that we use, they should not only consider the spatial arrangement of the fractures, but they should also be a multi-scale method. So to address those issues, we have used a method called Ripley's K function. Ripley's K function is a method of point pattern analysis that primarily applies to the distribution of discrete points or discrete events in the space. And we can use Ripley's K function to characterize a spatial organization of fractures in the subsurface. So here's the formulation shown here. So basically what it estimates is the expected number of points that fall within a search area that put on a random point inside a study domain. So if we know the area of the search area, and if we know the intensity of the points, we know how many points we should expect to see inside this circle. So if the number that we calculate using this equation for a specific pattern, if the number of neighbors is larger than what we expect to see from a random, then we call that spatial pattern cluster. If the number of neighbors is less than what we expect to see from a random distribution, then we call that pattern anti-cluster. So there's always a comparison made between what we calculate based on K function and what we expect to see from a random distribution. The nice thing about Ripley's K function is that we can do the analysis, we can perform a multi-scale analysis. So if we change the size of the circle, we can do the same calculations at another scale, and we can see if the, for example, clustering or anti-clustering changes from one scale to another. So as you can see, this method applies to data points. So before we can use it for fractures, we have to convert the fracture network to point patterns. There are several options. One of them is to replace fractures with the barycenters or midpoints. So when we replace fractures with the barycenters, we're actually, so the distance between the midpoints actually provides some information on how close the fractures are inside the network. Another approach is to use the fracture intersection points. So whenever two fractures cross each other or converge and intersect, we can put a point and then replace the whole fracture network with a distribution of intersection points inside the study domain. The advantage of looking at the distribution, a spatial distribution of the intersection points, is that it provides some information on the degree of connectivity over the entire study domain. Now that we have converted the fracture network to points, we can go ahead and apply the K function formulation to get figures like this. Let me explain how to interpret these figures. So on the x-axis, we have the length scale that goes from 1 to 1,000 meter. And on the x-axis, on the y-axis, we have the normalized K function. The shaded region is the confidence interval for a random arrangement. So if the line falls inside the shaded region, then the distribution is not distinguishable from random. But if it falls outside of the shaded region, for example, in this section, then the spatial organization is significantly or statistically significant. So for example, for the fracture midpoint at length scale less than 5 meter in this part, you can see that the red line falls outside of the shaded region. So the distribution is anti-clustered. At other length scales, it's inside the shaded region, so it's random. When we look at the fracture intersection points in the second example, we can see that the line is always above the confidence interval. So we can say that this specific pattern is clustered across all the length scales that we are interested in. So using Ripley's K function provides an opportunity to perform a multi-scale characterization of fractures to see if they are random, clustered, or anti-clustered. We can also use this information to model fractures or to generate fracture network realizations. So this is an ongoing part of the project, but I have some preliminary results to show. So this is the fracture networks that I showed on the first slide. So they have the exact same fracture segments, but they exhibit different spatial characteristics. The fracture network, which is distributed randomly, we can see a lot of red dots, and red dots are the intersection point. So the degree of connectivity is much higher in the random network than the original network on the left-hand side. So we developed an optimization algorithm based on random perturbation, which is shown on the right-hand side. The way that this optimization algorithm works is that we take the random network, the initial random network, and at each iteration step, we perturb the location of the fractures. We calculate the K function at various length scales, and then we compare it with the original network. If the mismatch is reduced, then we accept the new arrangement. If not, then we ignore it and we move on to the next iteration. We perform another perturbation. So at the end, we can convert the random network to a simulated network, which has the same spatial distribution of the fracture intersection points as that of the original network. Here is another example. So in the original network, most of the intersection points shown with the red dots are clustered on the left-hand side. But if you randomly distribute fractures, you can see that the intersection points are distributed over the entire study domain. But if we use the optimization algorithm, we can generate a simulated network which has spatially similar characteristic as that of the original network. So now that we know that the points or intersection points or the midpoints are spatially distributed similar to the original network, we have to make sure that they produce the same flow behavior. So what we are proposing is to convert the fracture networks or construct discrete fracture models for the for the original network, for the random network, and for the simulated network. Then we run a synthetic flow simulation models. So for example, in this case, I have an injection well located on the lower right corner and a production well located on the upper left corner of the simulation models. And after a specific number of simulations, you can see that in the random network, the water has already reached the production well because of the higher degree of connectivity between fractures, as are evident in this picture. But in the original and in the simulated fracture network, the waterfront is still far away from the producer. And this is also evident from the water production rates in which the water breakthrough occurs earlier than the other two network model. So to summarize, using method like Ripley's K function, we can characterize the spatial distribution of the fractures to see if they are random, clustered, or anti-clustered. And you can also use that information to generate representative or spatially similar fracture network realizations for further uncertainty analysis or other modeling purposes. With that, I finish the presentation and I would be happy to answer your questions. Thank you for your time.
Mahmoud, thank you very much. Appreciate your talk and appreciate, Mahmoud, I want to give you full credit. You weren't originally on the schedule and you said, I would really like to show this work this week. And you just jumped right to it. This is a great presentation. I appreciate you jumping in, showing the initiative.
Thanks for the opportunity.
Any questions from any of our participants? You know, I'm going to ask a question if nobody else does. What about, there's spatial point processes and then there's marked spatial point processes. A marked spatial point process includes not only spatial location, but also information like orientation and aperture. Have you given any thought to incorporating in the model orientation, aperture, other types of features?
Yes, so if I go back, let me see if I can. So if you look at, for example, these data points, they don't have any mark or label. So one of the approaches that we have used, and actually we have prepared the manuscript to submit to a journal, is that we can classify the data points or fractures based on the attribute that we're interested in. For example, if there's a threshold for aperture size, we can create two different classes, or if some of the fractures are like propped, some of them are open, we can generate different classes, and then we can perform the same spatial analysis on different classes to see if there is any attraction or repulsion, so to speak, between the fractures from different classes. So that would, instead of giving us information about clustering and anti-clustering, we can see if there is any attraction or synchrony or any repulsion or asynchrony between the different fractures from different classes or different sets.
And we might find out that there's no relationship. Turn out to be
exactly.
I have to say, one of the great things about this type of extension, use of spatial data analytics, is the fact that you'll find out often that there is not a significant relationship.
Correct. Yeah.
I think our eyes, our brains that have evolved over so many, hundreds of thousands of years, are very good at finding patterns in random.
Exactly. Yeah.
We can avoid making that mistake. All right. Any questions, comments? Mahmoud, thank you very much. Appreciate it.
Thank you so much.